Hi everyone. This is the eighth episode of Princeton Startup TV, and we are extremely honored to have Professor Robert Sedgewick on the program. Professor Sedgewick is the founder and former chairman of the Department of Computer Science. He is the William Baker Professor of Computer Science at Princeton, director at Adobe Systems, fellow of Association for Computing Machinery for the seminal work in the mathematical analysis of algorithms and pioneering research in algorithm animation. He's the author of numerous research papers and several books, including a series of textbooks on algorithms widely used all around the world. And we're extremely honored to have Professor Sedgewick on the program. Hi, Professor Sedgewick.
Hi, thank you.
Welcome. Thanks for being here.
No problem.
So let's start off with the following question. When did you decide to pursue computer science as a career?
Oh, at the time that I made the decision, computer science didn't exist. I was an applied math major. And I got a sophomore course in computing. And it was very clear at that time that it was a cool thing to do.
Right, and you completed your bachelor's at Brown.
At Brown, yeah.
Right, and then you decided to pursue your PhD at Stanford.
At Stanford, yeah, which was the only place that was offering a PhD.
Right. Very good, very interesting. I mean, one of the interesting pieces of a career is that you completed your PhD under the supervision of legendary Donald Knuth. What was it like to have him as an advisor?
It was great. I actually he didn't take very many students, and I wound up with him as an advisor by doing very well in a class.
Oh.
And then I was only a grad student for 3 years, so I only worked with him for a year and a half. But I met with him. It was just after Volume 3 came out. I read Volume 3.
I guess?
Yeah, 70. It came out in 72.
Yeah.
So a lot of my grad career was reading Volume 3 carefully.
Right. Do you agree with the fact that, do you agree with the quote, I think it's attributed to Donald Knuth, that the Art of Computer Programming is the most purchased but the least read book?
Yeah, that's probably true, yeah.
So, do you still interact with him?
Yes, I'm going to have lunch with him next Tuesday, actually.
Oh, really?
Yeah.
So you'll be in Palo Alto?
Yeah.
Very interesting. Do you agree with his quote, which I don't remember the exact interview, but he basically said, if the research topic is popular, it means that the results will be unimportant. Do you agree with this?
Oh, gee, I don't know about that. That sounds a little radical. I think he gets asked very often what were the most important results of the year and so forth. So maybe that's a little bit out of context, because I think usually his response is that all results are important,
exactly.
And everybody builds on everybody else's results. So it's very hard to identify one as more important than the other. I think it's more characterization of what he says.
Right. So in the there is this Nobel Prize effect in the research community when people get let's say some recognition, and then after that they cannot afford to work on small problems. They can only work on great problems, and then in the end it leads to the kind of decline in the in the number of important papers we publish and so on. And the same thing we can see. I mean, I've been reading this book by Clayton Christensen, Innovator's Dilemma, and we see the same thing in companies. The big companies cannot afford to work on these small, low-margin problems, and that's where disruption kicks in. That's why Google didn't notice Facebook, and Microsoft didn't notice Google, and all this, and so on. IBM didn't notice Microsoft, and so on, and so forth. What are your thoughts on this?
Let's see, from the academic side, I think it's more of a problem for a more mature field. I guess maybe computer science is getting more mature, but I don't really think so. I think it's barely begun. So I don't think it's a problem for us. There's so much to do. The problem for computer science in the academic side is that institutions have not invested sufficiently. everybody's computer science faculty should be twice what it is.
Mm-hmm.
And so everybody's been overburdened really from the beginning.
Right.
So we don't really have that effect, but that's the downside. The upside is you can work on almost anything and do something great.
Right.
Still nowadays. And that's one thing I try to get through in my teaching is that particularly young students are thinking, wow, it's all built. But actually, we're living with stuff that was built 30 years ago under very extreme circumstances. So do something better.
Right.
People in my generation, if we needed a text editor, we wrote it. Needed a typesetter, write it.
Yeah, and do you think it's useful, and have you experienced that in your career, research career, that this shift in a research area, let's say every 10 years or let's say every 7 years, is helpful to gain new perspective and kind of avoid this Nobel Prize effect?
I don't know. I think for us, it's more. It's more important to think about the future, and since everything is abstract, and really make a commitment to what goes on in the future. And there's in some areas people have been successful at doing that, but in other areas it's really disappointing to have new programming languages come out of industry, for example. It's not that big a deal to do a new programming language. There's a lot of interesting and fresh ideas, but I think there needs to be much more going on in academia. And the reason there isn't is that academia hasn't invested enough.
Like in terms of, do you see any trends in your research history that let's say in 70s you focused mainly on algorithms, shell sort, quick sort analysis of sorting algorithms, and maybe 80s you kind of switched to the visualization, I would say?
Well, no, there's the math. So
math.
Actually what I've really been doing is analytic combinatorics, which and that was a shift from doing analysis of algorithms, which is trying to understand fundamental properties of algorithms and be able to predict and compare performance, to analytic combinatorics, which is the underlying mathematics.
And that's the course you're teaching this semester?
I'm teaching it this semester, yeah.
Very interesting.
And so that's a big shift. And I work closely with Philippe Flageolet in France, and we wrote a big book on it, and so that's what I'm teaching out now.
If you, one of the, I guess, last questions which touch on this kind of your PhD time, when you were a PhD student, how do you allocate time for research, writing, and reading? This kind of a
it's not comparable to what you have today. I spend a huge amount of time in the library, looking stuff up, looking for stuff. So it's just absolutely. And then writing, we had my thesis was written by hand and then typed. So
is it available online somewhere?
Oh yeah, it's published. My thesis is published, a typed version.
Right.
And so it was a whole different process. Like writing a program, you punched it on cards and you got back the results the next day. So it was a totally different process.
Yeah. What was the collaboration environment like when you were doing your graduate work?
Oh, it was terrific because the field was taking off and everybody was doing exciting things. So that wasn't an issue at all.
Absolutely. So you kept your, I guess, doors open and to kind of kind of exchange ideas.
Sure.
So let's talk about the development of courses. Some of the courses you developed at Princeton. So the Introduction to Programming in Java, which I guess started in '92. How was the intro to CS was taught in Princeton before that, or was it?
It was like many other places, and the main feature is that at most places is that there's a separate course for every class of students.
Mm-hmm.
So there was programming for engineers, programming for civil engineers, programming for physicists, and whatever. So lots and lots of different courses. And then there was a CS course that taught programming for CS majors.
Mm-hmm.
And the problem with that approach is that only the CS majors are qualified for a second course.
Right.
And that we thought was a huge problem. So that's and there's that, and then there's just the responsibility to put a course out there like introductory physics or chemistry or biology that anybody coming to Princeton should be able to take.
Mm-hmm.
So that was the second part of the challenge.
So at this point, course 126, which is general computer science, is highest enrolled course at Princeton after economics, right? With
I think we maybe beat them now, but it's pretty close.
Pretty close, like 40% of all the students. I mean, stats
50.
Now 50%.
Yeah.
Okay. What's the percentage like for algorithms course?
25.
25%. So 25% of all the Princeton students take this course. What are the reasons behind the popularity of the two courses?
So the first one, we tried to appeal to everyone, and we leveraged their knowledge in science. So most intro CS courses are detailed features of a particular programming language suitable for cubicle dwellers, where ours is much more interesting problems or situations that one is going to confront in whatever field you go into, and computation as an essential way to address it.
So it's very example driven, very
always no toy problems at all. Whereas most CS courses or intro programming courses are just only toy examples. So like, and if you look at any book but ours, you won't find the sine function,
right?
Because that's considered too difficult. Well, high school students know the sine function.
Yeah.
So our first example of an array is sampling the sine function and then piping it into standard audio so you have music.
Yeah, all the course. So I tiered the course the previous semesters. All the assignments are really exciting. I mean, just make just students get really passionate about the subject.
There's that, and then there's they had no idea of any of the intellectual challenges, and also just demystifying the architecture. So we build the whole processor from the switch up, and they learn about intractability and computability and all the great ideas of our discipline.
Right.
And it's not that big a deal. In physics, they teach quantum, and chemistry, they teach extremely complex and difficult scientific concepts to first-year students. So why don't we do it? That was our idea.
Right. So you kind of
it appeals to students. So.
So you're solving this problem of like computer science students not knowing much about science and science students not knowing much about CS.
At the same time.
Right,
yeah.
at the same time.
Yeah, computer science students not knowing much about science, that was an objection. That we need to have a specialized course for our students. But really, a lot of computer scientists are kind of lost in abstraction nowadays. And they don't have any idea about the scientific method or about testing the performance of programs. And I think anybody using a computer should know some basic things.
Absolutely, absolutely.
So it's not harmful for them to see how computation is used in big variety of applications.
So the extremely popular series of algorithms textbooks, which were published, algorithms in Model, in Pascal, and C, C++, and then nowadays in Java.
Yep.
It aims to teach 50 algorithms, 50 plus algorithms, which every programmer should know. And so I've been a couple months ago, I saw this question on Quora. Someone asked, what are some great general algorithms books after Knuth, CLRS, and Sedgewick? And which definitely is just another example that this book, the algorithms book, is considered the standard many institutions. What, in your mind, are the reasons behind its popularity?
Again, the idea was to appeal to people who need algorithms and need to use them. The difference between my book and Knuth and CLRS is have actual implementations.
Yeah, you have actual.
And so it's bringing the implementation out into the light, and then also talking specifically about the scientific method and performance and testing performance. And particularly in the latest edition, that's explicit, and it's a big part of what we do. So therefore, people who are wanting to understand algorithms are actually working with implementations.
So humans are usually, kind of inductive. They can make generalizations after they see an example, after they see the motivation. And I found this book to be extremely helpful at this, and just kind of driven, motivation driven. You see this kind of problem which exists, let's say, in networks, and how do you say, and then it goes forward saying, okay, here's the minimum spanning tree problem, and that here's a prim algorithm, here's the Kruskal algorithm to solve it. It's absolutely helpful. Thanks for this.
And it's all goes together with the kind of math that I do and other things. I like the kind of math where I can check my math answer. So big O notation in the leading term is a bad thing.
Right.
It's considered harmful because you can't even check your math if you do that.
So in you mentioned this notion of galactic algorithm, the algorithm which will never be used in practice because any effect would never be noticed in this galaxy. Can you elaborate on that?
Log n is 5, and log star n is a much lower number. There's nothing wrong with basic research. There's nothing wrong with getting improvements in these types of factors. My problem is that people sometimes get those results, but in the opening paragraph or the closing paragraph, they'll say, this has the potential to be important in practice, when there's actually no way it would ever be noticed in practice. And so you shouldn't be making statements about potential implications when you know, if you're not disconnected from reality, that there's no way. And we have examples of this all the time. Award-winning papers that get an n to the 1/6 improvement in the worst case performance, with never implementing it.
And I guess you make this point clear in the 226, the algorithms course, that all notation is useful for many things, but it's not useful to predict performance.
It was actually developed by Poincaré as the basis for asymptotic series. So we use it in later terms, and it's supposed to indicate that we could get more terms if we wanted. The theoretical computer scientists co-opted that to also lump in worst case performance. So it's actually, the way it's used in computer science is really antithetical to the way it was developed. It was developed to indicate you could get more accuracy if you wanted. And so it's being misused.
Very true. So in the 2011 conference, like at Analco, the conference which last year was held in San Francisco, you had this talk titled "Algorithms for Masses," and then in that talk you hinted some you gave some pointers to where book publishing can go, and you mentioned the fact that the paper is written. I mean, the papers nowadays are not read on paper, unfortunately, but they're written still as if they will be read on paper. So can you elaborate on?
Well, I think particularly for publishing of scientific results, now most conferences don't print proceedings anymore. So they will put up on the web these abstract things that are kind of like paper, but they'll never be read on paper. Whereas, and that's an example, in my generation, somebody would look at that situation and say, okay, I'm going to write a scientific paper viewer editor for that will allow people to use color and motion and dynamics and other things in expressing their scientific ideas. And so it's going to be read on a vertical screen or a pad, or it should be device independent, and that's the way you should write it. And people should be exchanging ideas that way, whereas in computer science, people are looking at half renditions of PDFs. I think it's ridiculous.
So you're saying that in the years to come, if you mention the word simulation in a paragraph, there should be an actual simulation. There should be a Java, I guess, app or something.
Whatever. Or you could put a movie in, whatever you want. So I have that time, but my intent is to write a prototype for that, just to show what's possible, because it's so easy to do and to really be expressive, and make use of everything at your command to do these things, and for people to be just using existing tools and not worrying about how we're going to exchange scientific ideas.
Right.
I think it's a terrific lost opportunity.
It's again one of this kind of ambitiously frightening startup / research ideas which threaten your identity. That's why nobody kind of takes it.
You could decide to have total impact on the future of scientific publishing, and any individual could spend a year and get that to happen. So go for it. Right? I mean, that's what Knuth did with tech. That was one guy.
Wrote the entire thing, which is used by millions.
And so it's totally clear that something like this is going to happen, and it doesn't have to be done by a big company. It can be done by an individual. And when we were doing it, we were coding in assembly language on 32K machines. So it was difficult. Now you've got unbelievable resources at your disposal.
So at this point, your publishing model seems kind of a combination of the two worlds. You have traditional textbooks and the book sites, which is a pretty novel idea. And can you describe what your model is?
Sure. So we evolved to this model while developing the intro course. And whenever you do a book project like a book, you wind up having way more material than goes into the book. But we realized we could just put it on the web once we developed basic templates. So we just pour everything into the web. And then when it comes time to write the book, we can pick the best of it, tell the story, organize it. The web thing is dynamic. It keeps going. It's also got links. It's also got big data and other things that couldn't possibly go in a book. And we tell the students that the web is for use while you're coding. But if you really want to learn it for the first time or study for an exam, you can't beat the book, because that tells the story the way that you want to hear it. So that was a test, and then we did it for algorithms. It came out even better for algorithms, I think. We had 1.2 million unique visitors to the 126 site last year.
I think the main reason for this is, one of the few reasons is, last time I checked, if you just search 1 to 6, that's the top result in Google.
Well, if you search fft.java or other things like that, you get us.
The top results is many algorithms.
So and I think that's really going to expand and multiply, because nobody else on the web has anything close, and we're first there. We have 50,000 pages of stuff or more. It's going to be pretty tough for somebody to effectively compete with it. Not to mention the fact that big competitors like Knuth and CLRS don't have real code. And they have algorithms that you wouldn't even implement. So, not Knuth. Knuth is, I think I'm aligned with Knuth. He says he wouldn't even bother to write about something that he couldn't run on his desktop machine.
Very cool.
But many other books write about galactic algorithms, and
Yeah.
yeah, you're not going to put them on the web. The thing that I wind up getting the most questions about is people want to know, where's your implementation of Fibonacci heaps, say. Well, I couldn't imagine a situation where you would notice it in practice.
Yeah.
So why would I implement that?
True.
So
Yeah, I cannot easily conclusions. So you worked in Silicon. I mean, you're not only known as a researcher and professor, and you also worked as a software developer. So you have this kind of industry experience as well. You worked in Silicon Valley. What do you think are the most innovative companies nowadays?
Oh, Adobe.
Adobe.
Well, of
Yeah. Yes, conflict of interest. I
Yeah,
guess.
conflict of interest. Yeah, really be tough for me to single out
Yeah.
anybody. There's a lot of innovation going on in the Valley right now.
Right.
It's a very exciting time. I think I tell people it's as exciting as the 70s was.
What do you think of consumer web startups, consumer web companies like Facebook and Twitter, which kind of try to?
Yeah, I think it's hard to tell exactly what's going to happen. The entire web's going to get rebuilt over the next. I probably continually rebuilt as things work up. I'm not so sure about the importance of social, simply because they have to get privacy straightened out, and there are a lot of people who. There are plenty of people who love publishing publicly about their friends and so forth. But I got an email from saying that somebody's just turning 63 from Facebook. I don't think that person ever wants me to know that they just turned 63.
Especially
in fact,
women.
I'm pretty sure of it. Yeah, right. And I think that's going to be a serious problem. And the other thing is, once the ads start coming, people are not going to be as enthusiastic. I think, unless it's really carefully done.
So I guess for the aspiring entrepreneurs out there, some of the kind of startup ideas you outline is one of them being the kind of the new way to publish research papers. I mean, the kind of a new editor.
Well, I think more. I think more broadly,
yeah.
and I wouldn't think about how to make money. I'd think about what needs to be done. Yeah, how to make value.
That's the point.
And so there's writing papers, but there's also libraries themselves. There's a lot out there. How's it going to be organized and assimilated? And so I talked about this. Scientific papers is a pretty limited view, but it's a huge amount to do.
Yeah.
Like I want to have all the papers that I refer to in that one big ball of wax right there, so I can interconnect ideas. Or maybe it has to be done with smaller little factoids.
Right.
Maybe all my theorems should be packaged up and labeled so somebody else can get right to that theorem with one click. There's lots of things you could think about.
So it's a library for the collaborative library where you can just accumulate and share any sort of content, that's the kind of thing that's just needed.
And then there's social mechanisms there too. So one thing that people have done really well is conferences. So that's a couple of European grad students have implemented a couple of different systems that everybody uses, and that I think that's made that much more efficient. There's many more people participating than used to. But the actual publishing and exchange of ideas and the results, I'm not so strong on that, because I think that the papers are too dense and detailed. They're difficult to read on the web. I don't think people are exchanging ideas as effectively as they ought to.
So in this kind of potential kind of library for the web, do you see yourself as a researcher? And the researchers are usually, they try to kind of work on certain things in secret, kind of in stealth kind of mode. Do you think will researchers be comfortable with sharing kind of, let's say, articles they're reading right now?
Yeah, I think so.
Exploding right now.
Well,
So.
because that goes down to evaluation, and now people are starting to do evaluation by all kinds of web measures and links and other things like that. So yeah, there's a lot of innovation possible in terms of evaluating the impact of ideas. A little bit more than just counting citations. And so as those types of things become more important, then maybe the impact of holding on to your result until it's ready for the journal or conference, maybe it's a more of a cumulative thing than
so
that.
you can pre-publish it, get some feedback, and iterate on top.
Yeah, and publish it. What is publishing going to be? So we don't even know that.
Which so one of kind of our final question: which books do you read nowadays? If
I write.
You mostly write.
I've been writing, yeah. So
focus on being producer. Rather
well,
than
there's Knuth Volume 4.
Yeah.
That's going to take a little while to absorb.
Right.
What
about
in terms of technical? Yeah.
What about kind of for pleasure kind of?
Oh yeah, no, I'm always working. So.
Yeah. What do you apart from books? Do you read any technical blogs, and do you have any recommendations? Like, let's say some online, like, do you archive.org, for example?
No, I'm just always working. Yeah.
Try to kind of limit the files of this information. Very, very cool. And I guess the last question we have is, I know that it's understandably highly contextual, but what is your kind of piece of advice for people out there who haven't figured out what to do with their lives?
What to do with their lives?
So you can think that our target audience is fresh graduates. That's our.
I mean, it's unbelievable opportunities nowadays. So get yourself to New York City or Silicon Valley and go to grad school if you haven't been. There are really, really lots of opportunities. So take a job for a while and see if you like it. Or there's all kinds of startup opportunities available, and nowadays you can just do a lot on your own and try to make something happen. I'm not a big fan of working on an app and hoping to strike it rich that way.
Work on big problems.
Yeah, big problems, and get where the smart people are and work with them.
Thank you very much, Professor Sedgewick.
Thank you.
Big pleasure.
Okay.
It was Princeton Startup TV, episode number 8.